Hey guys, what's up? Eddie Aho here with KISSanalog.com. Okay, so today is the second course in this KISS University educational series. And what we're going to do is we're covering some basics right now. So we're going to try to go over this thing as quick as we can so we can get to the fun stuff where we're testing circuits and, you know, all the stuff we want to get to, right? So today we're going to jump into voltage, current, and what is it? Voltage, current, and resistance, right? Those are all terms we've heard of, and energy. And they're things we've heard about, so I think that's why we can go through things quickly. You know, we're not going to be tested, and we don't need to know how many electrons there are in an atom, that kind of thing. What we need to know is that there's free electrons in atoms, and we're gonna talk about this. Okay, so let's just jump into start talking. So, okay, where all this stuff comes from is an energy source, right? We know we get power energy from the power company to our home, and that's AC electricity. And we get DC power in our car from our car battery. So there's DC electricity. We get DC for our laptops and, you know, for lots of things, right? And we get AC for other things. So we're going to start talking DC, and then we'll start talking AC, and we'll kind of mix things up, and we'll do it where it makes sense. And wherever you guys have questions, let me know. And even if we have to jump back 3 or 4 classes, 10 or 20, whatever, we'll jump back and we'll have some additional videos to fill in some holes. So I'm sure if one person asks, then there's probably a whole lot more that want to know too. So please don't feel you know, don't hesitate, just write in, let me know, okay? All right, so let's talk about energy. Where does energy come from? Well, it comes from, you know, these days solar is a big thing. You know, everybody's kind of interested in solar, so that's a place where we get energy. We'll talk about those kind of solar cells later. Another thing is wind farms, right? If you drive down the freeway, if you go across states, you'll bound to go by some wind farms. So we pick up that way. We also get it from water. It goes through dams, right? It causes, you know, things to turn, and we create energy that way. Okay, so a lot of times energy is changing forms. You know, it might be chemical energy, like in a battery that we just talked about, into electrical energy, or it could be, let's stick with your car for a moment. So in your car, you put gasoline in it. That's chemical energy, and that's translated into mechanical energy. So, you know, and that's what moves the car down the road, right? Water, you know, is mechanical energy, and that turns into electrical energy. So the forms of energy is changing too. All right, so we get energy from a lot of different sources, and that's what gives us voltage, current, and stuff like that. So, what's voltage? What is voltage? I mean, what the heck? What's the definition of voltage? Well, let's first of all just finish up with energy. The definition of energy is the ability to do work. Okay, so the ability to do work. So now we know we have to have voltage. We get it when we plug cords into the wall, right? So what's voltage? Well, voltage is a potential difference. So what is that? All right, so voltage is like pressure. If you think about, often water is used to kind of explain electricity. So if you think about water in a river, if it flows up against a dam, there's a lot of pressure on that dam, and that pressure is voltage. Okay, or another way you think, maybe the gravity. You know, the pressure, the force is voltage. Okay, the water itself is current. That's what's flowing with the pressure. If there's no pressure, the water just sits there. Current doesn't flow, right? Just puddle. So where does current come from? Well, everything's made of atoms, and everything has electrons. So an atom is made of electrons, protons, and neutrons. We only really care about the protons and electrons because that's what causes the the flow of current. So an electron, there's on these atoms, the one thing we can talk about is there's different layers of electrons, and there's protons, and the atom wants to have the equal number of each one, so it's balanced and it's happy. Okay, the neutrons have no charge on them. Protons are positive, electrons are negative. So you want to have an equal number of positive and negative, and then they're happy. Well, when these electrons get further away from the nucleus, from the center of the atom, they call them free electrons. They can become free. They can be from chemical energy. All these other things can force those electrons to easily move away from the atom. And when it does, that atom says, well, heck, I want another electron. So it's positively charged now. So now it's charged positive, and this electron, it's gone to another atom, and that atom's negative now. So these electrons start moving around, and that's what gives us current flow. And what forces them to move around is voltage, is chemical energy, all these different things that cause energy that get these electrons moving around. So like in a battery, one plate gets charged up positive, one plate gets charged up negative, and it's the kind of materials and the kind of chemical processes they use that create these things. So alright, well, what allows the current to flow? Well, in water, it's riverbanks, right? A dam will hold the water back, but when you allow it to flow, it'll flow down a river, a creek, or whatever. So in electricity, on your batteries, you got cables hooked up to it, right? Those are what allow the current to flow into whatever is in your car that needs electricity. Or in your house, you know, your extension cords, your power cords, those wires. So, alright, so now we're getting to some other terms we've got to talk about: conductors and insulators. Conductors conduct, so seems fairly obvious. What makes a good conductor? Well, it's materials that have atoms that have lots of free electrons. Silver is an awesome one. We don't use silver a lot, because we do use it though, but we don't use it a lot because it's expensive, obviously, but also it's brittle, it's stiff. It wouldn't make very good power cords. So copper's more flexible. We like that. Copper is a very good conductor. It has lots of free electrons as well. So does gold, and gold is actually used in some of the old oscilloscopes. You'd open them up, they're works of art. But people would use gold. Now there's not a lot in there, there's just surfaces, but they'd use it because it doesn't oxidate. It doesn't oxidate. So that's awesome. You know, your contacts stay clean. So gold is and was good for that kind of stuff. It's not used as much. Well, you know, it's used in different places probably, but so you have silver, and actually for audiophiles, some, you know, I used to, gotta admit, I've bought that silver solder, where I would solder my terminals with silver, because I'd buy some silver stuff and I thought that was necessary. Anyway, so it's the old days when I was an audiophile kind of guy. But so you got silver, you got gold, and copper. Copper's inexpensive relatively to the others, and it's flexible like gold is. It's and that's another nice thing about gold, by the way. It's soft. So for contacts and so on, it's soft. It's malleable, you know, like copper is, and makes them good conductors because they have lots of free electrons. Current likes to flow in them, and they're flexible, easy to use. You know, there's all kinds of metals. Aluminum is used a lot, you know. Also flexible, and inexpensive. Not as good as copper, but a lot less expensive. So aluminum is used in a lot more wires today than, you know, than you might think. But okay, so then we have insulators. Well, you know, if you buy, or if you've seen wiring in a home, you know that there's plastic over those wires. There's usually 2 or 3 conductors inside those cables, and there's a lot of plastic there, right? That plastic, it's an insulator, of course, right? You know, the 2 wires, if they touch, they're gonna short. So a lot of us just know that as just, you know, so-called layman, you know, just it's common sense, kind of, you know, common knowledge, I guess. So that so some of this stuff's kind of obvious to us. So that's, you know, but it's good to cover it, just to, you know, to cover it, and because we're going to talk more in detail about some of this stuff. There's a thing called dielectric strength. That tells you how good your insulators are. On these wires, you might see printed on the side 300 volts. That means that, you know, you could put up 300 volts on 2 different wires. See, we talked about potential difference before. You know, 300 volts. You know, this wire might have 300 volts. This wire might be ground or return or 0 volts. So you got 300 volts of potential difference between those, and that insulator is guaranteed to stand up against that. So so we're going to talk more in detail about that kind of stuff as we go on. What else we need to talk about? Let's see, insulators, conductors. We talked about, all right, well, there's also semiconductors, right? We'll just briefly mention those. Semiconductors, I think a lot of us know what those are. You know, you hear about transistors or semiconductor plants, you know, computers. A lot of us, you know, with computers, a lot of us become more technical, even though we might not be aware of how technical we probably really are. But semiconductors, so they're kind of semiconductors. They aren't as good a conductor as copper and these wires we talked about, but they do conduct current. They do allow current to flow, and because they're kind of semi-conductive, they allow for some interesting processes to be made to turn them into these devices we use in our circuits. So we'll talk about that later, but just to mention it, just to say, hey, we got conductors, we got insulators, and we got semiconductors, something in between. All right, so now let's say you got this battery, and you got a wire, and you want to power up something. Well, you know, you could take some small wire like this and go power up a, you know, 10,000 watt you know, audio amplifier, right? Well, we know that, you know, if you're in the audio, these guys have big old gauge wires. Why do wires have to be so large? Well, because they do allow current to flow, but there's only, you know, they're not perfect conductors, you know. So what that means is that there is some resistance to the current flow. It's kind of like a riverbank. If a riverbank is only so big, it only allows so much water to flow. Like those dams I kind of mentioned before, when they open up those, you know, I forget what they call them, but when they open up the waterways to let the water out of the lake that they've created, they open them up so big, right? So they're resisting the flow to the big amount of water behind the dam. So that resistance to the current flow, to the water flow, is where we get resistors or resistance. And so then, okay, we have these things, we have these quantities, we have current, we have voltage, we have resistance. Well, how do we measure them? So resistance is in ohms. That was a German scientist, George Ohm, I believe his name. I've got some notes I'm going to show you guys. I'll show you my notes at the end, so in case you want to snap a shot of that, you can save that. Also, I'm going to refer to a kind of a simple, kind of a nice book that I'm going to kind of look at too. I'm going to use it for reference. I've got tons of books, so you know, I might reference some other books too, and if I do, I'll list those. But for now, I'll list this one book, and so you can follow that. Bought it on Amazon. It's fairly inexpensive. A bunch of my books are in my storage, which I got to empty out, and then I'll have access to a bunch of books. But anyway, this looked like a good book, and especially for these beginner, you know, kind of courses we're going to do. So what was I going to say? Oh, okay, the units. Resistance, George Ohm. So ohm, there's a Greek letter, the ohm symbol, you know, I don't know if you've seen it, but we'll you know, the next course we're going to start jotting down. We're going to start showing you a bunch of symbols and getting into a lot of that kind of stuff. We're going to start actually looking at some circuits the next course, okay? We're going to talk about Ohm's law, for instance. We just talked about Ohm, right? So Ohm's law. As a matter of fact, in the bottom of my notes here, I'm going to actually show you the first equation of Ohm's law that we're going to study. And by the way, I want to talk about math real quick before we talk about the rest of these terms. The math, it's not going to be a big deal, okay? You know, I'll simplify it. I used to teach some math. I used to teach electronics. So if you need some help in any way, just let me know. But you know, so if you can make change for $1, if you can calculate, gosh, there's a lot of things that we do with algebra that we don't even realize we're doing. And I think it's something you're interested in. You don't even realize you're using algebra. So I think this stuff will come fairly simple, and I'll help you, and hopefully I will make it easy. So anyway, okay, we got ohms. Okay, R is resistance. So okay, we got R, and how many R's do we have? Well, we're gonna have so many ohms. R is like 10 ohms. Let's say 1 ohm. Okay. Okay, then we need to talk about current. Okay, so current, it came from a French scientist, Andre Ampere, and so we call amps or amperes, but we use the letter A for that. And so when we say, well, what is current, we have, like in resistance, we have R is equal to ohms. Well, in current, we have I is equal to A, amps. So where's I come from? That's a French word for intensity, I believe. So that's where that comes from. All right, so then voltage, we talked about that. Now a lot of us have seen V for volts. That seems to be kind of obvious. But then there's E, and maybe you've seen E too. So now E comes from electromagnetic force, EMF. Often it's just called E these days. So we'll say E is equal to 10V. So the units are in V for volts. So we have, you know, E for volts. Like say E equals 1 volt. We might say, oh, 9-volt battery, E equals 9 volts. Okay, and then we say if we have a 100 ohm resistor, R is equal to 100 ohms. And if we have 10 amps, you know, we say I is equal to 10A or 10 amps. So that's how that goes. All right, now when they come up with a yardstick or a foot, 12 inches a foot, I don't know, how did they come up with that? You know, so when they came up with units for these things we're talking about, what they did is they figured out, they said, well, you know what, let's do it this way. Let's say that we have 1 volt and we have 1 ohm of resistance, and that means we have 1 amp of current that we allow to flow through that wire. So if you have 1 volt and your wire has 1 ohm of resistance, you'll have 1 amp flow. So everything was unity. Unity meaning 1. So that way, made math easy. It makes it all start. So anyway, so that's unity. So 1 volt, 1 ohm is 1 amp. When we do some math, we might have to figure out how many ohms we have. So we'll say well, we had 1 volt, we had 1 amp, and we'll use this equation called Ohm's law, and we'll say, oh, that comes out to 1 ohm. Okay, so depending on what those numbers are, and we'll show you those equations. It's kind of funny because these 3 things we can manipulate around this equation, just move them around and come up with the answer. So once you learn how to do it for one, you know how to do it for the other ones. So yeah, makes it pretty easy. Okay, so let's see, did we cover everything for this course? Alright, so I think that covers it for this. I think that was a good kind of introductory to terms and kind of explain a few things. And the next time we're going to start, now that we know what ohms, volts, and amps are, we're going to start looking at those on schematics. We're going to actually start drawing schematics and see how that goes. But before we go there, one thing I do want to mention, just put the bug in your head, just to, you know, because we'll hit on these subjects over and over and over. So I just want to talk about current flow. We talked about it, right? You know, back in the day when they learned about voltage and current and resistance, the thing that they didn't really understand, they didn't really understand it down to the atomic level, meaning the electron level. So, you know, they just thought, hey, current's going from this plus thing to this minus thing, and they started polarizing things with plus and minus, okay? And they kind of understood this, and they thought, okay, so that was the convention, okay? Well then, when they got down to the atomic level, and they thought, or they realized, oh wow, it's actually these electrons moving around, and the electrons are actually going from this negative charge thing all the way around to this positive charge thing. Well, by then the symbols and the schematics and a lot of the things were being used were already drawn the other way, and so people say, well, that was the old convention. Well, so people said, well, okay, but this makes sense to us, even though it's backwards. It was thought to be, you know, that's one way to say it, it's backwards. They said, well, we're going to call that conventional flow. We're just going to go by that. We like conventional flow. And then other people said, well, we're going to follow the electrons, so we're going to call it electron flow. So there's these 2 schools of thoughts, okay? As a matter of fact, you can buy books. One will be conventional flow. It'll have all the arrows drawn plus to minus, and the other one will have the arrows opposite way. It makes no difference how you understand it. You follow one or follow the other. That's the way it is. But I'll tell you what I think it really is. I think the way it works in practice, I know that it's kind of funny because people like to have debates about this sometimes. You know, because like, hey, I know how electrons flow. I follow electron flow. But I'll tell you what, schematics are drawn with the plus voltages on top and the negatives on the bottom, or the returns on the bottom. And when you draw a schematic, you'll have the input come to the, you know, the input power, the signals will come to the left side of the schematic just by convention. Just that's the way we do things. And outputs will be on the right side of the circuit. So it's kind of like reading a book, left to right, top to bottom. So we start top left corner and kind of move through it that way. So it just, you know, it's just natural to look at a circuit in a schematic, you know, without even thinking electron flow or conventional flow, and to think about it as conventional flow. So I really think that most people, if not, you know, I mean, you never can say all, but I'd say most people look at a schematic and look at the flow of things in the conventional manner, which is, there's absolutely zero wrong with that. I think when you get down to the transistor level, this guy's getting warm. So when you get down to the transistor level, say a tube, where you're actually looking at, you know the electrons are gathering on this plate and they're jumping over here. When you get down to that level, then you're really looking at the electrons, how they're moving and what's going on, you know. But that's kind of the microscopic level, I'd say, where the macro level, where we're looking at schematic, we're troubleshooting, I would say most cases and we probably, even in some cases, troubleshooting, we go back and forth without even thinking about it. So it's one of those things. Once you understand it, you know. So yeah, I just wanted to let you know the difference between convention and electron flow. Another way to think about it, if you're standing in a line and you're a bunch of electrons and you're waiting to get in the movie theater, every time the person steps in front of you, the electron in front of you steps up, then you step up to fill that hole, right? Well, that hole just moved behind you, and the next electron stepped in that one, the hole moved back again. So as electrons are going this way, holes are going this way. So it's just another way to think about it. So there is actually something moving that way. I don't know. Anyway, it doesn't matter. So it's nothing to worry about. When we're talking about this stuff, you might stumble on that thing if someone's tried to explain electron flow to you, and I'll try to explain the difference as we go along too, so that you're never confused. Okay. All right. Hey, just wanted to throw that in there. Okay. Hey, thanks guys. We'll see you next time. Hopefully in a couple days. Okay, so just go over some notes that I made myself and that might help you. Is we're just covering the intro to the basic voltage, amps, and resistor terms. We kind of talked about energy, the kind of forms, and the voltage, electromagnetic force, current, and some notes about the scientists. And about conventional flow, we talked about that, and electron flow, and what conductors are, and insulators. Okay, let me scroll down so you can see the rest of it, okay? So conductors, insulation, resistance, and semiconductors, a little comment about those, and the relationship of volts, amps, and resistance. 1 volt divided by 1 resistance is equal to 1 amp. So we're going to talk about this, but that's the beginning of Ohm's law. Okay, kind of a intro to the next topic we're going to cover. Okay, hopefully that'll be in a couple days.